So then what? V total of 0.3. Let's make this 0.3 here. 9 over 3 minus 9 over 3. 0 volts. And then V total of 0.4 is going to be what? 9 over. So actually, that's interesting. The potential at infinity is 0. The potential at the middle is 0 too. So they're both at the same potential. So it's kind of like saying you have a hill. At a certain point, the level is plateau, then it's a valley. And then at infinity, it's also plateaus. The terrain plateaus. So infinity is plateau, over there is plateau. If you put a ball in that plateau, it's not going to go anywhere. Okay? So, actually, this one is actually... you know what? In this case, if you put a charge over here, is it going to go nowhere, or is it going to move? This one will push it. This one will attract it. So the hill valley analogy didn't work. Let me see here. Hill valley. Oh, yeah, here it is. Just because you have a hill and a valley and the elevation at a certain height is 0, just because the elevation at a certain height is 0 doesn't mean the ball ain't going to go anywhere. So I was wrong when I said the ball ain't going to go anywhere. If you put the ball at the elevation of 0, well, if there is an elevation less than 0, the ball is going to go to the elevation less than 0. You see? Same thing there. You put the charge in the middle, it's going to go towards the negative. You see? Okay, so V total over here is going to be, it should be 9 over 2 minus 9 over 4, so it should be 2.25 volts. And then V total 5 is going to be pretty much the opposite of that, 7.2 volts. Now, if you really look at it, let's see, 7.2, the difference between the potential of this point and that point, okay, the difference of the potential between these 2 points became 14.4 volts. Right? That means over here, something about my argument was wrong. My difference here is 12 volts. When I started out with 8 volts, 12.5, 14, 15.5, 20. The difference between those two potentials, I got 12. So my argument there is wrong. Why? What did I do wrong there? What I did wrong is that the increments I was using, these increments, 4.5, 1.5, 1.5, 4.5, those increments were true only if you have a single charge, right? If you have a single charge, 1 nanocoulomb, 1 meter away, 2 meters away, 3 meters away, the increments were 4.5, 1.5, so on, you know. And then I put 2 charges. I tried to use 4.5, 1.5, and then back to 4.5, back to 1. You can't do that. Those increments only work for 1 charge. Okay? So if you got 2 charges, Don't even try to do that. You just have to take the potential of each, add them, and then the increments now are going to be, from here to here is going to be about 5 volts. See, from here to here is 5 volts. From here to here is 0, so it's a 2.25 volts. So this is an increment of 2 1/4, increment of 5, back to 2 1/4, back to 5. But the general pattern is still true. The increment from here to here is more. It's about 5 volts. The increment from here to here is 2 volts. I'm rounding it now. From here to here is 2 volts. And then from here to here is 5 volts. Now, if we knew the actual size of the charge, we could go to the surface of the charge, right? And we could say whatever the size of the charge is, but this increment would be definitely more than 5, right? So that pattern would work. So today I wanted to concentrate on more trying to give you what the potential means rather than going to just the math of it and everything. You know, what does potential mean? What is it trying to get at? Now, there's something else known as potential energy.